All right, let's jump right in. Our world is just constantly in motion, right? Everything is always changing. But what if I told you there's a secret language, a mathematical one, that can actually describe and even predict all of that change? Well, today, we're going to decode that language. We're talking about partial differential equations.
I mean, think about it. It sounds kind of impossible, doesn't it? Trying to predict things that are changing not just over time, but across space, too. How on earth do you write a formula for something that's different everywhere, all at the same time? Well, it turns out that all these things, a rumor spreading, sugar dissolving, heat moving through a spoon, they seem totally unrelated, but they can all be described by the exact same kind of mathematical tool. They all play by a fundamental set of rules, and that tool is the partial differential equation, or as you'll hear it called, a PDE.
Now, here's the really cool part. To build these super powerful equations, we only need two core ideas. That's it, just two. And the first one is something you already get deep down. It's basically a simple accounting rule that runs the entire universe.
Just think of it like a bank account for anything. The change in your balance is just whatever comes in minus whatever goes out plus any interest that gets generated inside, right? It's this universal balancing act. It has to add up.
So, to track all this, we got to get two terms straight. First, you have the stock. That's the amount of something you have at one specific moment, like the total heat in a spoon. And then you have the flow. That's the rate that the stock is moving around, like the heat traveling up the handle. The conservation law is what connects these two. And of course, mathematicians have this beautiful, elegant way to write that whole idea down. Here, U is our stock, and that phi symbol, that's the flow. That little div thingy is just a way of measuring how much the flow is spreading out from any single point. So the equation is literally just saying the change in the stock is perfectly balanced by its flow and any new stuff being created.
Uh-oh, we've hit a snag. This amazing universal rule gives us one equation, but we have two things we don't know: the stock, U, and the flow, phi. You can't solve an equation with two unknowns. We can't predict the future yet. We're missing a piece of the puzzle.
And that, my friends, brings us to our second core idea. To solve this puzzle, we need to know something about the actual stuff we're looking at. We need to understand its its personality.
This is what's called a constitutive law. Now, this isn't some universal rule. It's a specific description that comes from watching how a particular substance behaves in the real world. Does it get carried along in a river? Does it just like to spread out on its own? This is the law that tells us how the material connects its own stock to its own flow.
Let's look at a few personalities. If you have some pollutant in a river, its flow depends on the river's current, right? It gets carried along. That's convection. But sugar dissolving in coffee, it spreads out all by itself, moving from where there's a lot of sugar to where there's less. That's diffusion. That grad symbol just points in the direction where things are changing the fastest. So for diffusion, the law says the flow moves away from the lumpy, high concentration areas. And hey, look at that. Heat flow and diffusion, they have the exact same personality.
Okay, so we have our two pieces, the universal accounting rule and the material-specific personality. Now it's time for the magic trick. We're going to put them together and forge a master equation that can actually tell us the future.
So check this out. We start with our conservation law, the one with two unknowns. Then we grab our constitutive law. Let's use the one for diffusion, which gives us a neat formula for the flow, phi. All we do is substitute that formula for phi right into the first equation. And poof, just like that, the flow variable is gone.
And what we're left with is the famous diffusion equation. We did it. We now have one equation with only one unknown, U. That little triangle, by the way, the Laplacian, it's just a way of measuring how lumpy the stock is. Basically, the difference between one spot and the average of its neighbors. By combining a universal law with a specific observation, we've built ourselves a genuine predictive engine.
And what's so wild is that this method doesn't just create this one equation. It unlocks an entire family of equations. It gives us a whole language for describing all the different ways our universe works. You can think about it like this. Just like in geometry, you have fundamental shapes, circles, squares, triangles. PDEs have their own fundamental types. And each type describes a totally distinct kind of behavior you see in the real world.
So the main families are actually named after the conic sections you might remember from high school math. You've got elliptic equations, which describe things that are balanced and in a steady state. You have parabolic equations, like our diffusion example, which describe processes that smooth themselves out over time.
And then you have hyperbolic equations, which describe things that travel in waves, keeping their shape as they go.
And this leads us to some of the absolute rock stars of science. This is the wave equation. It describes everything from a vibrating guitar string to how light itself moves through the vacuum of space. It's the classic hyperbolic PDE.
Then there's this beauty, the Laplace equation. It's a cornerstone of elliptic PDEs. It describes things that have settled into a perfect equilibrium, like the final shape of a soap bubble or the gravitational field in empty space.
And just to show you how mind-bendingly far this goes, this is the Schrödinger equation. It is a PDE, and it is the absolute foundation of quantum mechanics. It describes the weird, wave-like nature of reality at the tiniest, most fundamental scale we know.
And what's so incredible, what's just so profound about all of this, is that all of it, from the heat in your coffee spoon to the very fabric of quantum reality, all that complexity boils down to just two simple ideas.
That's it, a universal conservation law and a material-specific personality. We've used them to find the equations for waves and heat and even particles. So the real question is, what other parts of our world are out there, right now, just waiting for us to figure out their equation?